Hi, everyone, and welcome back to part 2 of the Keystone Ecology Review. We're going to start out with biomagnification. In biomagnification, toxins move from lower levels in the food chain to higher levels. So for example, let's say that there's a toxin like mercury in the water. You can see that there's 1, 2, 3, 4, 5 mercury pieces in the blocks of water. Now, what happens is that phytoplankton live inside the water, and they pick up the mercury as they move and filter the water. So there is more mercury inside the plankton or phytoplankton than there is inside the water. Fish eat many, many phytoplankton, thousands a day potentially. So there is then more of the mercury toxin inside the fish than there is in the lower level. Birds eat many fish, thereby building up the biotoxin even further. The problem is that humans like to eat things that are at the top of the food chain. We like to eat, say, fish, and we like to eat fowl. So when we're eating it, we're not eating the water that has a very limited amount of the toxin. We're eating the bird where the toxin has collected. Many of these toxins are very harmful to human health. So for example, if you've ever seen Alice in Wonderland, you know the term mad as a hatter. Mercury poison can break down material in the brain, causing you to exhibit symptoms of a crazy or erratic nature. So again, the higher up we go in the food chain, the more toxin there is. Mostly humans are not eating things like phytoplankton, we're eating things like fish and birds. So we need to sometimes limit the amount of them that they eat so that this biotoxin doesn't build up in us too, because most organisms do not have the ability to push or get rid of this toxin naturally. Carbon cycle. The carbon cycle has many subcycles inside it. What we want to talk about first are some of these reserves. There are long-term carbon sinks and short-term carbon sinks. Long-term are ones where it will be there for more than 100 years. Things like the atmosphere, the ocean and other water, coral reefs, coal, oil, and natural gas, or fossil fuels, however you'd like to think about it. These things hold on to lots of carbon, and generally the cycle is in balance. The atmosphere has been sharing carbon with the ocean, which has been sharing carbon back with the atmosphere for a very long time. Now remember, carbon dioxide might be the most famous part of the carbon cycle, but things like methane, fats, glucose, and other sugars can all be part of the carbon cycle because they contain carbon. There are other natural parts of the carbon cycle, like the one that we've studied in our class, respiration versus photosynthesis. Remember, in the photosynthetic equation, carbon dioxide in the atmosphere is getting uptaken by plants, which make it into glucose, which is then eaten by animals. The animals then respire the carbon dioxide back into the atmosphere, which is uptaken by plants that build themselves, which are eaten by animals and respired back into the atmosphere. There are other ones that are in balance too. Volcanic eruptions and forest fires are natural things that are meant to put carbon and other carbon products into the atmosphere, which will then end up being uptaken by plants and other photosynthesizers, such as phytoplankton in the oceans. The problem is that we are burning oil, coal, and natural gas, and thus putting carbon that has not been in the atmosphere for millions of years out there. This coal, oil, and natural gas fossil fuel burning is the unbalancing factor in the carbon cycle. We'll talk about that more when we get to global climate change a little bit later in the presentation. So again, short-term carbon sinks hold onto carbon for less than 100 years, like plants and animals. Long-term carbon sinks hold on to large amounts of carbon for a long period of time. Atmosphere, water, soil, ocean sedimentary rock. There are ways that we can impact our carbon cycle and help to limit the amount of fossil fuels that we're using. That's called carbon footprint. I'm going to give you just a few minutes to read about ways to reduce your carbon footprint. If I go too fast, you can pause the video so that you can view this slide a little bit longer. The water cycle. This is probably one of the cycles that you are the most familiar with. And when we look at the water cycle, one thing that we want to start with understanding is that water has to essentially go against gravity. To do this, we need the sun. The sun is the energy source that drives the water cycle. So let's start with evaporation. Water evaporates into the atmosphere. It is then condensed into clouds, where eventually it becomes so heavy that gravity drags it down via precipitation. That water will either run off, go back to the body of water it came from, or infiltrate into the ground where it will find its way into groundwater or other aquifers. When it does infiltrate into the ground, it can also be absorbed by plants, where it will undergo another form of evaporation called evapotranspiration, or just transpiration for short. In this way, water vapor leaves plants and enters the atmosphere, where it can condense and precipitate again. Humans also are part of the water cycle. We drink water, we eat water through plants and animals, and we respire back into the atmosphere. Remember, the other half of the respiration equation, not only do we put out carbon dioxide, but we also put out water vapor as well. The nitrogen cycle. The nitrogen cycle is pretty complicated, so we're going to try to pare it down pretty hard. Nitrogen in the atmosphere is not accessible easily. It's because nitrogen atoms, the N2 here, are triple covalently bonded together. It makes it really hard to get those apart. So what we need is this thing called nitrogen fixation. And this is driven by bacteria. We're really lucky to have them. Nitrogen fixing bacteria can turn atmospheric nitrogen into other items inside the soil. This can be ammonium, NH4, ammonia, NH3, nitrite, NO2, or nitrate, NO3. We don't really need to get into how these very specific compounds interact with nature, but suffice to say, they're going to end up entering plants where humans can eat them. These can be things like legumes or peanuts or other items that then allow omnivores and herbivores to eat these plants and uptake that nitrogen so that we can use it to build ourselves. Of course, it's a cycle. So there are other bacteria that take the compounds that were made underground and turn them back into atmospheric nitrogen. Carbon dioxide. I said that we'd start to cover a little bit more about the anthropogenic part of the carbon cycle. The greenhouse effect is good. We want it. It's what allows Earth to be a temperature that allows humans to survive here. The problem is that we're putting out too much carbon by burning fossil fuels. When we do this, we don't allow enough solar radiation to escape back out into the void of space. So over here on the left-hand side, we can see how we do have a natural portion of the greenhouse effect. Solar radiation comes in, it's absorbed by Earth. It's then re-radiated, some escapes into space a lot, and a little bit bounces back. This portion here is the greenhouse effect. It's natural, it's healthy, and it keeps Earth at a good temperature for humans, plants, and other animals to survive. When we add extra greenhouse gases, things like carbon dioxide, water vapor, methane, and others, do you notice how this arrow changes size and how the Earth heats up? So solar radiation comes in, the same amount as would naturally, but more of it is absorbed by Earth and re-radiated. A lot more of that then bounces off the layers of the atmosphere, comes back and gets a second chance to warm Earth. So the anthropogenic or man-made greenhouse effect is a problem. The natural greenhouse effect is a good thing. How does that relate to global climate change? Here is a picture of how temperatures on Earth have been changing. They're changing faster at the top and the bottom of Earth, or in other words, at the North Pole and the South Pole. They're changing more slowly in the center. But if you notice, there is nowhere on Earth that is, or very few places on Earth that are having no change at all. Some of these white ones are changing at an average pace, but that doesn't mean that they're not getting warmer. It just means that they're getting warmer at a more moderated rate than the top and the bottom of the globe. This is a problem because as the globe gets warmer, we end up seeing a temperature instability. In other words, rain changes its patterns. Places may get a lot more rain than they need, while other places may get a lot less rain than they need. This is also bad because certain areas are good at growing crops and certain areas are not. And so if areas, say, that are a desert today end up being temperature and climate-wise appropriate for growing crops, we can't just move the crops and grow them there. So this could lead to food instability as well. The way that we can change this is to change away from fossil fuels, to moderate our use of that, and to work hard to limit other anthropogenic or human created gases that are getting into the atmosphere, allowing the planet to warm. Remember, greenhouse effect is part of climate change, but climate change is bigger than the greenhouse effect. Invasive species. Here are some pictures of invasive species. And invasive species are species that move into an area and outcompete the native species. The problem with this is that there are usually not predators for these species in their new home. And so without the force of competition, they grow and change way out of proportion. These pigs, you can see how many offspring they have. This is because they don't have their natural predators that they would have in Asia and Europe to keep their numbers down. We all know this guy, this is the stink bug. He doesn't have his Asian predators, and so he feeds on crops and other things that farmers are using to sell. This is purple loosestrife. You can see how it's the only thing in the picture. The problem with invasives like this is that they're really beautiful and they look lovely, but they're not eaten or consumed by any animal in America. And so the plants that should be growing here, that should be feeding the butterflies, the beetles, the bees, the fish, and other organisms that live here like turtles, they don't eat this. So this is essentially a food desert for the organisms that are supposed to live here. This is the Burmese python. Burmese pythons will eat anything that fits in their mouth, and they've actually been known to throw up food so that they can go out and hunt again. They hunt many native and endangered species into extinction. Pollution. Atmospheric pollution, other than just the carbon ones, can come from many sources: natural, mobile, stationary, or areas like cities, and even in rural areas where we use things like fertilizers. The more pollution we put out, the more it builds up in the atmosphere. And this can lead to things like human health crises, because older people and younger people and people who already have health concerns are very susceptible to emissions that go out into the atmosphere. We can have things like particulate matter. The smaller the particulate matter, the more dangerous it is to humans. Larger particulate matter is of a less concern because it cannot get into the lungs and potentially pass into the bloodstream as easily as small ones. Nitrogen dioxide is a smog-causing item. It can turn the air over cities yellow, and it can mesh up with fog to create smog. So it's partially particulate matter, partially things like nitrogen dioxide, but all of these things are not healthy for humans to be breathing in. Other ones are things like SO2. And SO2, when it comes from mobile and other stationary items like power plants, will go up into the atmosphere and will cause acid rain. When it rains down acid rain, this can kill small animals and plants and make the biodiversity of entire biosphere more limited. So the bottom line is that there are many sources of pollution, but that they all are a human health concern because they add together to create pollutant emissions in the air that humans, animals breathe in, and that lead to not just things like global climate change, but to things like emphysema or COPD or other breathing disorders. Limiting factors. This is our last slide. If you look at the animal that is in the center of this picture, what we want to think about are what are ways that he might die In other words, how is he potentially not going to be able to access items in his environment that may be in a limited way, and that if other organisms uptake those resources, he may or may not live? I picked this particular picture because some of them are obvious. If you notice, there's not a lot of water. If he's not able to find a water source, then he will die of thirst. Look at the really dry brush that's in this area. If he's not able to find a good amount of food, again, he is a grazing herbivore, he will pass away. If he cannot find a mate, or if he fights with another male, these are all limiting factors that might cause him to die and another organism to live.